everyone, my name is Nikita Mishra. I'm a senior at Cal State Los Angeles. Today I'll be presenting my current project, Computational Characterizations of Binding Affinity in SARS-CoV-2 Variants to the human hACE2 receptor. My advisor is Dr. Forzesh from the Computer Science Department. And now I know what today is going to look like. I'm going to go through an introduction to provide some context and background to my project, explain our methods and approach, and then discuss the results we have so far. Then I'll wrap up with a short conclusion and where we plan to take the project in the future. So let's get started. So in this project, we are examining SARS-CoV-2, which is the virus that causes COVID-19. Now, this virus will bind to the human ACE2 receptor in the lungs via the receptor binding domain of the virus, or the RBD. The interaction between the RBD and ACE2 has been animated at the bottom of the screen here, and it has an associated change in the binding free energy. Now, the binding free energy is a really important characteristic of the binding nature of the virus to the receptor, and it can be characterized both experimentally and computationally. And so within the actual RBD of the virus, there are thousands of possible mutations. These mutations are also known as single nucleotide polymorphisms, or SNPs, and they can cause changes in the binding mechanism of the virus to the receptor because they can alter the value of the binding free energy. When this value is changed, it can impact the viral biology that different variants present with. So what I mean by this is that some SNPs may change the BFE such that the virus becomes more infectious, causes more severe disease. We saw that with the Delta variant compared to previous variants. SNPs might also cause the BFE to change such that there is an increase in the transmissibility of the virus, which is something we've been seeing recently with the Omicron variant and the subvariant BA2. SNPs in the RBD have, been a really important factor in causing the breakthrough infections that we've been, hearing about for the past year of the pandemic. And it's really important to be able to characterize the BFE values of these mutations because it can elucidate a lot about the nature of new variants. However, when we go to actually, find the value of the BFE for different mutations, we run into a bit of a problem. I mentioned to you earlier that the binding free energy can be characterized, experimentally, but that's a pretty difficult process. It's laborious, it's time consuming, and because of that, it's not very scalable. We can't really study the thousands of mutations that are possible within the RBD easily. So to, sort of remedy this, we can bring our issue at hand into the computational space. And here we can create a computational protocol that will study the mutations of SARS-CoV-2 in a way that is consistent, efficient, and accurate. So with all this in mind, I'm now going to go into how we are, approaching this problem and how we've been developing our computational approach. On this slide here, I've shown the specific settings of our pipeline, and there are a couple of main things I want to point out. First, we are using a method known as MMGBSA, which is the abbreviated form of Molecular Mechanics Generalized Boron Solvation Surface Area. The general workflow for MMGBSA has been shown on the bottom left of the screen here. So we begin with the initial structure and then run it in an empty simulation. From that, we extract snapshots of both the unbound and bound states of the virus and receptor. And then we calculate the binding free energy for each of those snapshots. Then we take the average of all of those free energies, and that's the value that's reported by MMGBSA. The other thing I want to point out here is we are using a method known as alanine scanning mutagenesis for the actual mutations. So this is a process in which we, take the residues that are in the receptor binding domain of the virus and just change them to alanine. This is reflective of, the sort of natural process because in nature we often see amino acids get, changed into alanine by single point mutations. On the bottom right of the screen here, I've shown the residues that we've selected for study so far. These residues are all part of the receptor binding domain of the virus and are also involved in hydrogen bonding for SARS-CoV-2. So on the next slide, we have here the actual flow of the pipeline. We began with the wild type files upon which we run an MD simulation and extract coordinates, very similar to the first, steps I showed in the MMGBSA workflow on the last slide. Then we can begin working with the mutations. So we, select a location we would like to mutate, generate the mutant topology files and the associated input file, which will have pointers that will tell the program where the mutation is happening. Then we can actually run MMGBSA and produce the value for the change in the free energy. There are a couple of points I want to make here. First, this process can be automated from end to end. So the user would just input the location of the mutation, then we automate these last three steps here to then just provide the user with the value that they're looking for. Now, the reason I say we only need to automate these last three steps is because we can actually maintain the wild type trajectory and coordinates across all of our mutations. So we don't need to repeat these steps every time we have a new mutation to study, which is great because that will speed up our calculation time. Now, the other part of our research has been comparing the values that we get to other techniques. So that includes computational approaches, as shown on the left side here, and also an experimental approach, which is shown on the bottom of the screen. So that's our approach, and so now I'm going to discuss what we've done with this approach, what we've gotten so far. So our wild type studies were the first step in our process, and we obtained our sort of baseline free energy value. Now here we're only considering the enthalpic contribution, and what we got for the wild type from our pipeline was negative 61.73 kilocal per mole plus or minus 0.34. Now this was really promising because the value that we obtained falls right between the range from two other reference papers that also calculated the free energy computationally, and our error was also quite low. So with this, we were encouraged and we continued on with our mutation studies. And now on this slide, I've shown three of the mutations that we have studied thus far in this first round, as well as the DDG that we have calculated. So that's the relative change in the binding free energy. And as we can see, the DDGs that our pipeline calculated for these residues estimate the binding free energy a little bit better than another computational reference. We can take, for instance, this phenylalanine residue, which the DDG that the pipeline gave us was negative 1.35 kilocal per mole, which was much closer to the experimental 0.46 than the computational reference was. On the next slide, I've shown two things here. First is just this figure from the methods section to sort of just help visualize, where the mutations that we are actually performing actually are in the virus. And this graph is actually the comparison between the computational reference DDG in orange, our DDG in gray, as well as the experimental DDG in yellow. We can see that there are a few locations where our DDG, is a better estimation and others where it's not. So we've been working on optimizations to improve our pipeline and improve the accuracy. With that, I'm going to get into the conclusion. So herein I presented to you an end-to-end automated pipeline that examines the relative BFE changes and mutations for SARS-CoV-2 with MMGBS. Future work includes improving the accuracy, as I mentioned to you, wrapping up feasibility studies, doing the automation, and then migrating all of it onto a web server that would be very user-friendly and easy, open access. Okay, that is my presentation. I appreciate your time and your attention, and I look forward to answering any questions that you might have.